Welcome to this new module on diffraction due to and slits diffraction grating. So diffraction grating can be defined as an optical device consisting of either a glass or polished metal surface over which thousands of fine equidistant closely spaced parallel lines are drawn with the help of a diamond cutter. So that means we can draw those lines either on a glass plate, parallel and equidistant lines with the help of diamond cutter, or the same can be drawn on a polished metal surface. So there are four types of diffraction gratings: master grating, original grating, from which we can make replica, and again we can define it as transmission grating and reflection grating. So let us discuss these things one by one. So first of all, how a master grating is created, let us try to find out. So before drawing with the help of diamond cutter, if you look at the side view of the glass plate, it looks like this. So no lines are drawn, a plain transparent glass plate. When you draw lines on this with the help of diamond cutter, parallel and equidistant lines are drawn with the help of diamond cutter. What happens is whenever we draw a line, that region becomes opaque, non-transparent, and the region between these two lines acts like a slit, transparent slit. So like that, it is going to have n number of slits. So if you directly draw lines on the plain glass plate, it becomes a master grating. And over the master grating, if you pour this cellulose acetate chemical, cellulose acetate chemical, and we will allow some time to settle down, and after that we will peel off this cellulose acetate. So this is the field of cellulose acetate. So this cellulose acetate is packed between two glass plates. So such type of thing we will call as replica. Right? So we have covered what is a master grating and what is a replica type of grating. So most of the things which we use in lab are of replica type. Then further we can define, I told you it is as a transmission grating and a reflection grating. If source is one side and the diffraction pattern is other side, so what does it mean? This grating is acting like a transmission type. So lines drawn on a glass acts like a transmission type of grating. Whereas if you draw lines on a polished metal surface, so what happens? It is not going to allow the light to the other side. So the incident light and the reflected light are both on the same side. That type of things we will call as reflection grating. So totally on the preparation, master grating and replica grating, and how they are working out, we can classify them as transmission grating and reflection grating. Grating element. So we can define grating element as the distance between consecutive slits of a grating. And if E is the width of the transparent region, and if you assume D as the width of opaque region or non-transparent region, so grating element is the distance between the centers of two non-transparent regions or transparent regions. So here I told you E is the transparent region. So center to center of the transparent regions, the half of this width is E by 2, and opaque region is D, and again the half of the transparent region E by 2. So the total together it becomes E plus D, and this E by D we will call as grating element. So what does grating element stands for? It is the distance between the centers of two adjacent transparent regions or two adjacent non-transparent regions also. Right? So that we will call as grating element. And if there are n number of lines for unit length, the grating element and number of lines can be related as E plus D. Grating element is equal to 1 by n, where n stands for number of lines on the grating. In this picture you can see we have three different types of gratings. One having 100 lines per millimeter, the other one 200 lines per millimeter, the other one is 300 lines per millimeter. So the area is same for all this for millimeter. In millimeter area how many lines we are trying? 100 lines only we are trying. And coming to here for millimeter area we are trying 200 lines. Whereas in the same millimeter we are going to draw 300 lines. So what does it mean? The space is remaining same, but the number of lines drawn is increasing. When the number of lines drawn is going to increase, what happens? E plus d value is going to decrease. To call a grating as a good quality, the minimum requirement is 15,000 lines per inch. As you know, 1 inch is equivalent to 2.54 centimeters. So let us take three different types of gratings. One is 10,000 lines per inch. Second one is 15,000 lines per inch. And third one is 30,000 lines per inch. So this is capital N. So let us look at E plus D. So what is how we can get E plus D? 2.54, because the area is remaining fixed 2.54 by 10,000. So it is going to be almost 2.54 into 10 power minus 4 centimeters. So because we have drawn only 10,000 lines per inch. If you draw 15,000 lines per inch, it is 1.68 into 10 power minus 4 centimeters. And if you go for 30,000 lines, it is going to be 0.84 into 10 power minus 4 centimeters. So what does it mean? If the number of lines n is increasing, E plus D value is going to decrease. So this E plus D is equal to 1 by n. Now the diffraction due to end slits. That means a diffraction gate can be imagined as a diffraction due to end slits. So let us consider a diffraction grating X Y of having so many slits A, B, C, D, E, F, G, H, I, J, K, L, so on. So these are the slits on the grating. This is our screen. So a wavelet WW dash is incident on this diffraction grating. So the secondary wavelets traveling in the direction of incident light will focus at P0. That means all these lines which are these secondary waves after coming but from the slit, all these secondary waves which are moving in the direction of incident light. This is the incident light and this is the diffracted light. Both are making theta is equal to 0 degrees. All those things are converging at point P0 on the screen. And you see S1, S2, S3, S4, so on to Sn, S1 P0 to Sn P0, all are traveling the same path. There is no path difference in this race. That's why certainly this point is good. P0 is going to be a central maximum. Now consider the secondary wavelets that are traveling in a direction inclined at an angle theta. Earlier theta is equal to 0. This is theta is equal to 0 degrees direction. Now the thing which we are considering here is theta not equal to 0. With incident line will reach point at P1 in different phases. You see S1 P1 and Sn P1, they are not traveling the same path. There is some path difference. There is lying some path difference. So as a result, dark and bright bands on both sides of central maximum are obtained. Now let us try to find out what is the intensity at point P1. It may be considered by applying the theory of Fraunhofer diffraction at a single slit. Already we discussed about single slit. By using the same analogy, we are going to talk about these end slits. So here the wavelets proceeding from all points of this grating in a slit along the direction are equivalent to a single wave. This is a single wave for a single slit for us. This is a single slit for us. This is a single slit. Like that, how many single slits we have? N number of single slits we have. From each single slit, the amplitude already we know A sin alpha by alpha. So from every single slit, we are going to get a wave of amplitude A sin alpha by alpha starting from the middle point of the slit. If there are n slits, then we have n diffracted waves. Then the path difference between these two consecutive slits, if you take this slit and this slit, these are the two consecutive slits. What is the distance between this to this? Already we know it is E plus D. So this is the path difference. That path difference, how much? Sin theta. Sin theta. So let me assume this as S1 and this as S2, and this is S1K. Sin theta opposite S1 S2K by hypotenuse S1 S2. Already you know that S1 S2 is the distance between the centers of two transparent regions. Just now we discussed that it is equivalent to E plus D. So what happens? S2K path difference becomes equivalent to 2 pi by lambda into E plus. So path difference becomes equivalent to how much? First of all, path difference only we'll talk, then we'll go for the phase difference. So S2K is the path difference, and this S2K is equal to E plus D into sin theta. So let us convert this path difference S2K into corresponding phase difference. So phase difference D is equal to 2 pi by lambda into E plus D sin theta. Let us assume this as 2 beta. Hence, the intensity in direction theta can be found finding the resultant amplitude of n vibrations, each vibration of amplitude A sin alpha by alpha, and the phase difference between two adjacent vectors is 2 beta. So, what we are going to do is, already we know that the resultant amplitude formula, what is that? R is equal to A sin n d by 2 by sin d by 2. Here, instead of A, we will substitute A sin alpha by alpha. Instead of small n, we will substitute a capital N number of vectors. Instead of small d, we will substitute 2 beta. So that what happens? So R is equal to, so what is the resultant amplitude? R is equal to A sin n d by 2 by sin d by 2. So what we told? Instead of small a, that is replaced with A sin alpha by alpha. Instead of small m, we replaced capital N. So d by 2, what is d? 2 beta. 2 beta by 2 is nothing but beta. So what is the resultant amplitude at point P1 is R is equal to A sin alpha by alpha sin n beta by sin beta. And we know that intensity is square of the amplitude. So that's why A sin alpha by alpha whole square sin square n beta by sin square beta. In the first term, A sin alpha by alpha whole square is the diffraction term due to single slit, and the next term sin square n beta by sin beta is the resultant of n vectors. So let us look at the principal maxima when we are able to get this as A sin alpha by alpha whole square. So according to L'Hospital's rules, limit beta tends to m pi, sin n beta by beta whole square is equal to n square. That means if you apply L'Hospital's rule here, what happens? Here limit sin n beta by sin beta becomes 1, or limit sin n beta by beta whole square becomes n square. So I is equal to n square into A sin alpha by alpha whole square, that is intensity. Or if you write R, n times of A sin alpha by alpha. So the single slit amplitude is A sin alpha by alpha and multiply with the n number of slits. So the resultant amplitude n times of A sin alpha by alpha. So when you substitute L'Hospital rules, it becomes n square. So I is equal to I naught sin square alpha by alpha square n square. And for beta tends to m pi. What is beta? Beta is equal to 2 pi by lambda into E plus D sin theta. Should be equivalent to n pi. So pi cancel. So what we are going to get, E plus D sin theta is equal to L lambda is the condition for central maxima, and this E plus D sin theta is equal to N lambda is known as grating equation. In our laboratory for the diffraction grating experiment, the formula we are deriving from this E plus D sin theta is equal to n lambda. From this, lambda is equal to e plus d into sin theta by small n. But you know, e plus d is equal to how much? 1 by n. So e plus d also I am replacing with this 1 by n. So sin theta by small n into capital N. So this is the formula which we are using in the diffraction grating experiment. What is that? Sin theta by small n into capital N, where small n represents the order, capital N represents the number of lines on grating. And coming to the minima, it should become 0, and this is going to become 0 when sin n beta is equal to 0. And this n beta becomes 0 only when n beta is equal to plus or minus n pi. Substituting beta value, n beta, n into e plus d sin theta, pi into e plus d sin theta by lambda is equal to m pi. Again, pi cancel. N into e plus d sin theta is equal to plus or minus m lambda is the minima condition. So like that, we in this module we finished diffraction due to end slits. So far we talked about diffraction due to single slit, diffraction due to double slit, and in this we talked about diffraction due to end slits. Thank you.